Hi, I'm Tom Dick. I'm a math professor and a math advisor for Texas Instruments. This short video is part of the TI-Nspire AP Calculus series, and here we're going to take a look at how you can use the TI-Nspire to practice graphical derivative analysis. Now that's a skill very useful for the AP exams because the type of problem that you'll often see on the free response questions is the presentation of some graphical function that's the derivative of another function. Good example of this is the common question AB3 BC3 on the 2018 free response questions. You're then asked questions about analyzing the behavior of the function given that derivative. Now the file we're going to be using is called PWL derivative, that's for piecewise linear derivative, and it really gives you an opportunity to get practice with this idea. Here's an example problem. Suppose we wanted to create a piecewise linear graph of a function f that's the derivative of another function g. We want g to have a relative minimum at -1, relative maximum at +1, and we want its graph to have an inflection point at x equals 0. Now let's go over to this PWL derivative file and see how it works. We're going to be able to manipulate the graph of a continuous piecewise linear function f by simply moving some points around. Using fundamental theorem of calculus, the function g, which is a definite integral function of our piecewise linear function f, will give us an antiderivative of that, and we'll be able to see the graph of g on the same page. Okay, here's where we've got to start, and we've got our function y equals little f, and notice this is a very simple function. It's just a straight constant function, y equals 1. Now you see this shaded area, looks like a rectangle. Well, that's representing the value of the integral from a to x. A and x are linked to sliders. The value of a is -1, the value of x is +1 currently. And our function g, the values are given by the definite integral from a to x of little f of t. Now I can change the value of x by clicking on the slider, and we can see that's moving a point along the graph of g. I can also change the value of a, but I want you to note that the value of a is tied into the definition of g, and that's actually changing our entire function g. In fact, what it's doing is it's moving that graph up and down. Okay, so we've got this really handy way to see the graph of an antiderivative of that function little f. And I want you to note that it does do definite integral values. I'm moving the value of x now to the left of a, and because the integral from a to x is running from right to left, the area of that rectangle, we need to take the negative of it to get the value of the integral. And notice the value of g of x for x equal -2 is -2. We've counted that area as negative since we moved from left to right. Now you can see I can manipulate my function little f by just dragging some of those marked points. So I drug the point at x equal -2 down from the value it had to below the x-axis. And now I've got a brand new function g because it responded immediately to the changes I made in little f. And this graph's a lot more interesting. It's not just a straight linear graph anymore. So let's think about what kinds of properties g has by analyzing its derivative, little f. Now as I look at the graph of little f, I see that it changes values from positive to negative at x equal -3. And that means we should see a local maximum at x equal -3 on the graph of little g. Now over at x equal -1, my graph of little f changes from negative to positive, which means the graph of its antiderivative, little g, should display a local minimum there. Now where the graph of little f changes slope from negative to positive here at x equal -2, that's going to correspond to a change in the sign of the second derivative of g, which means we have a change of concavity and an inflection point there. Now, keeping those kinds of ideas in mind, let's go back to our task. We want to create a piecewise linear graph of f that our function g has relative minimum at -1, a relative max at +1, and inflection point at 0. Now, the graph we left off with already had a relative minimum at x = -1, so that's nice. I'm just going to drag this point down so we don't have an extra maximum over there at x = -3. Now I still need to get a relative maximum over at +1. So what I've done is drug the graph so they cross the axis from positive to negative there. And I'm getting rid of any extraneous extrema by dragging the rest of the graph below the axis. So we've got a relative min at x = -1, relative max at +1, and we also have an inflection point at x = 0, because that's where our graph this time has changed slope from positive to negative. That's little f, which means the second derivative of g has changed sign, giving us that inflection point at x = 0. So we have satisfied all the requirements for our function g. Okay, why don't we try another example? Our new function task is the following. We want to create a function little f so that its antiderivative, g, has the following properties. Its graph needs to be concave up and decreasing for the interval -4 less than x less than -2. We want our function g to be constant between -2 and 0. And we want the graph of g to be concave down and decreasing for 0 less than x less than 4. Finally, we want g of 2 to be equal to 0. Okay, to accomplish these things, first I'm going to concentrate on that interval from -2 to 0, because if g is going to be constant over that interval, that's going to mean my derivative graph has to be exactly equal to 0 from -2 to 0. Now it looks like we're already good from -4 to -2, because my derivative graph is increasing and negative. That means the graph of g will be concave up and decreasing. Great, now we have the constant function between -2 and 0. And we've also got concave down decreasing from 0 to 4. And we accomplish that by making our derivative graph negative and decreasing. Now I still need to get the value of g of 2 equal to 0. How are we going to do that? Well, we don't want to change any of these other properties we worked so hard to get. Actually, all we need to do is change that lower limit of integration to a = 2. That'll automatically make g of 2 equal to 0. All the other properties stay the same. So this function g satisfies all the properties we were looking for. For more calculus resources like these, see education.ti.com.